let's talk about the Doppler effect. Now, you guys were looking at this in lab, and you noticed that if we have a source that's vibrating, it produces waves in all directions around it, and those waves have a constant wavelength as long as this thing is a periodic motion, lambda, and they move with a constant speed v, and they have a constant frequency f. But if we put this object in motion that's creating these waves, say it's moving this way, then these waves tend to pile up on each other, and so our lambda gets short. Now, the velocity of the wave doesn't change, but there is something going on there, and the frequency goes up. Okay? Whereas on the other side, these waves appear to be stretched out, and again, the velocity of the wave doesn't change, but the wavelength is longer, and the frequency is lower. Okay? Now, what this means to us is if we have a sound producing object go by us. As it approaches us, we hear this side of it, which makes it a higher note. As it goes by us, we hear this side of it, which makes it a lower note. So we have this change in frequency, not because the source is actually changing frequency, but because the wave is sort of being manipulated by the relative motion of the source versus us. So what we want to do is take a look at how we can mathematically deal with that. And to do that, we're going to take a look at two pictures. Okay, so if I have a source, it produces a wave, and the distance the wave moves in the period of the wave is the lambda. Okay, so the distance the wave moves, d, is equal to the wavelength as long as t is equal to period. But this isn't the only motion that's going on. If this thing is also moving, then by the time it produces its next wave, it's actually a little bit closer to us. So this next wave is being produced here when our original wave is still only here. So our wavelength was effectively shortened by this. Okay, so this is our new wavelength, lambda prime, and we have this distance that it's different. So what I'm interested in is what is lambda prime? How do I get it? Well, lambda prime is equal to the original distance, lambda, minus however far the source went in this time. And I'm going to call that ds. Okay, so lambda minus the distance the source went. Okay, well, how do I figure out how far the distance the source went? Well, I need to know how fast it's moving. So the velocity of the source is vs, and the distance it goes is equal to velocity times time, as long as it's moving at a constant rate. So ds is actually equal to the velocity of the source times period. Now, if we think about this a little bit, we can actually rearrange our equation so it's all in terms of velocity of the wave, velocity of the source, and wavelength. Okay, because remember, the velocity of a wave is given by wavelength times frequency, or the velocity of the wave is wavelength over period. So if I have the period in here, I can replace that. T is equal to the wavelength divided by the velocity of the wave. So this velocity is the velocity of the wave, which is going to be constant as long as it's going through the same medium all the time. So I'm going to go ahead and simplify this a little bit more, and I'm going to say, or maybe make it more complicated, the new wavelength, lambda prime, is given by the original wavelength, lambda, minus Vs times t, but Vs doesn't change, but t I'm going to change to lambda over the velocity of the wave. Now the good part about this is now I can pull out that lambda. So lambda prime, the new wavelength, is given by the original wavelength times 1 minus Vs over V. So this lets me find the new wavelength. Now this equation applies only when the source is moving towards us. So here's us, this is getting closer to us. If the source was moving away from us, if it was moving this way, then instead of a longer or a shorter wave, we would now have a longer wave, and it would be longer by ds. So all we'd have to do is change this to a plus, which changes this to a plus, which changes this to a plus. So this is for moving towards. Okay. If we want to know about the lambda prime for moving away, we just change that one sign and we have 1 plus Vs over V. Again, that's the velocity of the source divided by the velocity of the wave, and this works for moving away. Now, we derived these all in terms of wavelength, but a lot of times we're actually more worried about frequency, or we know more about frequency. So all we have to do is make the substitution for frequency. Now remember, frequency is equal to the inverse of period, okay, Or if we have, let's do this a different way, V equals wavelength. Ugh, why would I write a W? V equals wavelength times frequency. So if I want to make a replacement for frequency, what I want to do is I want to solve this equation. So the velocity of the wave is not changing, but because we have a new apparent wavelength, lambda prime, we're going to get a new apparent frequency, frequency prime. So we're going to substitute this equation in here and solve it for frequency. I'm not going to bore you with all the algebra, but essentially what we get is f prime, the new frequency, is given by f over 1 minus Vs, there's a 1 there, the velocity of the source divided by the velocity of the wave. This again, this is the negative case. This is when they're moving towards the stationary observer. Okay, and I'm sure you guessed by now that f prime for away is equal to f divided by 1 plus Vs over V. And so this is when it's moving away from a stationary observer. These four equations, or two, however you want to look at it, can be used to calculate what an observer would hear due to the motion of a source. Okay, and they're messy. The worst part is there's a whole nother set of equations for if the source is constant but the observer is moving. So again, I'm going to go to a picture. We have the source staying right here, producing waves like this. Okay? Now, there's two cases to look at. There's two cases to look at. If the observer is moving towards these waves, then he's actually getting to them more often than if he was at rest. So he has effectively shortened the wavelength. And so our new wavelength, lambda prime, is really given by the original wavelength minus the wavelength or the distance ds that he's moved, and so then we'd have lambda prime is equal to lambda minus the velocity of the observer now, so this is the velocity of the observer times period, and that gives us the new wavelength, and then we can go through some similar math as before to actually end up with our new wavelength in terms of velocities. So this is lambda prime is equal to lambda times V naught, and then T, V equals wavelength times frequency, right? So, or over T, so T equals V over, or lambda over V. So I would replace this with lambda over V, and then I have this new equation, lambda prime equals lambda minus V naught, or V observer, that's not naught, that's an O for observer, lambda over V, and I can simplify that. Lambda prime, the new wavelength, is equal to lambda, the original wavelength, times 1 minus V over, or the velocity of the observer over the velocity of the wave. So now I have the velocity of the observer instead of the velocity of the source. This has changed a little bit, but it's a very similar process. So let's just go ahead and get you these equations. The new frequency is given by the new velocity, which, okay, so, whoa, that was weird. Okay, erase. Okay, so the new frequency is given by 1 plus V naught over V times the original frequency, and this is if the observer is moving towards the stationary source. So you'll notice this is actually going to increase our frequency because this is moving together. We're going to have, like, here we have a shorter wavelength or a higher frequency. So this is towards the source. Okay. If we're going away, then f prime is equal to 1 minus V observer over velocity of the wave times the original frequency, or the frequency of the source. And so this is for moving away from it. And you'll notice this is going to lower my frequency or increase my wavelength, which does follow. Now, these equations get messy, and there's a lot of them, and I don't really want you to memorize them all. But I don't want you to have to drive them all again either. So what we end up with is we can actually combine those two equations into one that says the new frequency is given by the original frequency times, and here's the messy part, v plus or minus the velocity of the observer over v. Remember, these unsigned v's are the velocity of the wave minus plus the velocity of the source. Okay, now why plus minus and minus plus? Well, because it depends on the relative motion of these things. If they're moving towards each other, if towards, then use the top sign. If apart, bottom sign. Okay. There's actually one other way we can try to write this, but we have to then put another caveat on it. Okay, so you can write this as the new frequency, the frequency that the detector hears or the observer hears, is given by the frequency of the source. I guess I could note that, times the velocity of the wave minus the velocity of the observer over the velocity of the wave minus the velocity of the source. Now you'll notice I dropped the pluses out of this, but this equation only holds when you have a positive velocity for the source. If you set up your frame, if you set up the frame, the reference frame, so that v, the velocity of the wave, is always positive. Okay? So if you think about that, okay, then here's the source, and it produces a wave, and if that wave is moving this way, then that's my positive direction. So if I'm moving away, then the velocity of the observer is also positive. Okay, if the source is moving this way, it's also positive. So we look at the velocity of the way the wave is moving, and we make that our positive direction. You'll notice if we were worried about stuff on the other side, then my positive direction switches to this direction. So you do have to keep in mind which way is positive and negative if you use it this way, but there's less signs to remember. If you use it this way, then again, you have to know if are we moving apart or are we moving together. Okay? So I'll show you an example problem in another video.